maybe I can start by reminding you of what we're doing because we're kind of in the middle of one big calculation, right? So you remember that we were talking about bound states versus unbound states, which is a distinction that happens in classical mechanics and also in quantum mechanics. Okay, and the unbound states are also called scattering states. All right, so we talked about that distinction in general, and we talked about how some kinds of potential energy have only bound states, like the first two things that we studied, the particle in a 1D box and the harmonic oscillator. And by comparison, when we have the free particle, it has only unbound states. And then the idea was, can we design a potential that will have both? Okay, and so that's our goal for the moment. Okay, and so the first thing that I thought of designing was the golf course. Well, actually, the first thing was the hydrogen atom, but that's too hard for now. And then the second thing was the golf course, where the potential energy V of x is just flat, and then a little hole, and then flat. And then one simplification of the golf course was to do the delta function potential, where we take the width of the potential to be extremely narrow and the depth to be extremely deep. And then that limit looks like a downward pointing spike. Okay, so V of x as a function of x looks like it's 0 all the way to there, and then goes to infinity, and then goes back to 0. Okay, so this delta function is what we were working on in the last class. Okay, and so in the last class, we worked on trying to calculate, can there be any bound states for a potential like this? So that means, can there be any states where there's a negative energy, and so the particle has to be confined near x equals 0? And at first you might guess, no, there can't be any bound states because the potential is too narrow. But if that's your guess, then you're wrong. Okay. Or you might guess, oh, there could be an infinite number of bound states because the potential is infinitely deep. But if that's your guess, you're wrong too. Okay, because in fact, we did the calculation on Thursday and we found there's exactly one counted bound state. Okay, and there is one bound state which has a particular energy and a particular wave function. Okay, so let me find it in my notes. Okay, so we found there is one bound state, and the wave function is psi of x is this b e to the minus kappa absolute value of x, and that is with a certain value of kappa. That is, kappa is m alpha over h bar squared. Okay, and then this state has a certain energy, okay? And the energy is negative h bar squared kappa squared over 2m. So that comes to negative m alpha squared over 2 h bar squared. This is a particular state with a particular value of kappa, right? So one value of kappa that is consistent with the way we had to join the two solutions at x equals 0. Right? And then this b is, I didn't say it on Thursday, but I should say it now. The b is determined by the normalization in the same way as everything else we've done in this semester. That is, we want to say that the integral from minus infinity to infinity of psi star psi dx equals 1. If you do that, what you find is that b has to be the square root of kappa. So the square root of m alpha over h bar. Okay, so this is the one bound state. Right? And what can we do with this, right? Well, for one thing, we can check the units to make sure we haven't made any mistakes. Okay, that would be a good check. That's always a good check. Okay, so you remember, if we want to check the units, the potential energy is negative alpha delta of x. All right, and so the potential energy, this has units of energy. Delta of x has units of 1 over length. Therefore, this parameter alpha has to have units of energy times length. Okay, so let's see about the units of this thing. Okay, so up here we have mass and then alpha squared, so that's energy squared times length squared, and divided by h bar. Okay, so h bar has units of energy times time, or position, length times momentum, right? So h bar for energy squared times time squared. Let's see if we cancel these energy squareds. And then mass times length squared divided by time squared. That's like mv squared, right? Like in that kinetic energy, right? So this is indeed energy. Oh, good. So that works. Okay. So it tells us that the bound state, the one and only bound state, has a particular negative energy relative to 0. 0 is the energy for the particle to escape to infinity. Okay, so it has less energy than that. Okay, And then it has a particular wave function. And the wave function is this thing up there. So if we plot it, whoops, wrong pen. If we plot the wave function as a function of x, it is decreasing like this. Okay. And so that means that the particle is confined to be near x equals 0. Okay, so that doesn't mean the particle is stuck in the hole, because the hole has no width, right? This is a delta function potential, right? It's right here with no width. So the particle can't be in there, but the particle has to be close to there. It has to be near x equals 0, and it cannot get too far away. And how near does it have to be? Well, we can say, how rapidly does the wave function die off? Okay, and so if you go out to a distance of x equals 1 over kappa, then the wave function is down by a factor of 1 over e. Okay, so at this distance, say psi is reduced by a factor of 1 over e. Okay, and so that means that the probability density, which is psi squared, is reduced by a factor of 1 over e squared. So that means that the probability of being at a distance, in a little interval of distance around here is about 1/6 of the probability of being in a little interval of distance around there. So the particle is concentrated in a distance between -1 over kappa, -1 over kappa and +1 over kappa. And, it would be a good homework problem or a test problem to say, what's the probability that the particle is between -1 over kappa and +1 over kappa, right? So that would be like, what's the area under the probability density between those 2 points? I don't think I put that on the last homework, but I could put it on the next test. Okay, so good. So that is the bound state. Okay. Now that is half the calculation. Okay, we still have to do the other half, right? So we want to figure out what kinds of states can there be for positive energy, right? So what we did so far was case 1, assume E is less than 0. Check, we got that. Okay, so now let's do case 2. Assume E is greater than 0. Okay. So we want to figure out what kinds of states can there be with a positive energy. So that's another whole calculation. Okay, I'm going to do part of the calculation right now, and then I'm going to take a break to talk about what is a scattering state anyway, and why do we use the word scattering? And then I'll go back and finish the calculation after that little break. Okay, so let's do some of the calculations. So we have to remember how we were working on the calculation on Thursday last week. Okay, so remember we are solving the time-independent Schrodinger equation. Okay, so the time-independent Schrodinger equation is that negative h bar squared over 2m times the second derivative of the wave function minus alpha delta of x, that's the potential energy, times the wave function, is equal to E times the wave function. Okay, and we can, it's hard to solve this with a delta function singularity right in the middle of our solution domain. So we can break into two regions, okay? And so we're gonna break into the regions of x negative and x positive. And we'll solve it in those two regions and then connect up the solutions, right, at x equals 0, using the method that I showed you on Thursday of just integrating from one side of the delta function to the other side. Okay, so if we break into those two regions, then for x negative, we have this negative h bar squared over 2m. This second derivative is equal to E psi, because the delta function is negative. No, because the delta function is 0, excuse me. X is negative, so the delta function is 0. And for x positive, it's exactly the same equation. Okay, so last week we considered the case where E is negative. And so now we're doing the case where E is positive. Okay, so we have this kind of equation where the second derivative of psi is a negative number 2me over h bar squared times psi itself. And that's for negative x and positive x. So we've solved this before, right? We know how to solve it, right? That is, we let this coefficient, let's call that k squared, okay? Same as we did for the free particle, right? And then we know what the solutions are, right? Because if the second derivative is a negative number times psi, then the solutions have to be sines or cosines, or the solutions could be complex exponentials with a plus ix and a minus, plus ikx and a minus ikx. Let's do the complex exponentials, okay? That worked out well for the free particle. And we could see with the free particle that the complex exponentials had a nice interpretation in terms of a particle going to the right or a particle going to the left. All right, so we could say solutions are complex exponentials. Okay, so that means for x negative, we could say psi of x is equal to a e to the ikx plus b e to the minus ikx. And I'll say with k as a positive number. Okay, so these are two solutions. One is a wave moving to the right, the other is a wave moving to the left. Okay, and then for x positive, psi of x is the same kinds of complex exponentials, but it could have different coefficients. Okay, same as we allowed for the possibility of different coefficients for the bound state. Okay, so let's say it's f e to the ikx plus g e to the minus ikx. Okay, now we want to see what kinds of boundary conditions can we apply. Okay. Well, first of all, can we apply boundary conditions at infinity, right? So we did in the bound state calculation, right? We had a boundary condition that the particle's wave function could not blow up as we go to x is infinity or minus infinity, right? It had to be normalizable there. Right? Here, we can't really apply a boundary condition like that, right? There's no risk of the wave function blowing up, right? A complex exponential oscillates, it doesn't blow up. So that's not a problem, right? We have the same problem of normalization as we did with the free particle, but we found ways to deal with that. Okay. So we could say there's no boundary conditions at x is plus or minus infinity. We don't get any extra information from that. Okay. Now, what about at x equals 0? At x equals 0, that's the place where we need to join these two solutions. Now, you remember that one requirement from last week was that psi must be continuous. At x equals 0. And that goes along with the whole formalism of Schrodinger's equation. That is, if the equation has a second derivative in it, then the first derivative must be defined everywhere. And so the function has to be continuous, that first derivative defined. Okay, so that means that psi has to be the same on the two sides of x equals 0. Okay. So what do we have on the negative side? All right, so on the negative side, if x is slightly negative, then we're using this equation up here, and we plug in x equals 0, and that gives us a plus b. Similarly, if x is slightly positive, then we need to use this equation, and we can plug in x goes to 0 over there, and we get f plus g. Okay. So that gives us one constraint on these four coefficients, okay, that a plus b has to equal f plus g in order for our function to be continuous. Okay, now what about the derivative of psi, the first derivative of psi? Well, we worked out last time what happens if we integrate Schrödinger's equation. If we integrate Schrödinger's equation from x equals 0 minus epsilon to x equals 0 plus epsilon, where epsilon is some tiny little number, that showed us that there has to be a discontinuity in d psi dx at x equals 0. And the discontinuity, has a particular magnitude. Okay, so what we worked out from this integrating Schrödinger's equation across the delta function is that minus h bar squared over 2m. And so then we had the first derivative at plus epsilon minus the first derivative at negative epsilon. So this is the discontinuity in the first derivative. So this thing minus alpha times psi at 0 is equal to 0. So that's the equation that we derived last week. Okay? And then last week, we plugged in the bound state wave function as the psi. Okay. Now let's plug in this other expression for the wave function. Okay. So we're going to plug in the derivatives of that on the positive side and the negative side. Okay, this works, but it's kind of a pain. Okay, so let's I don't know, I'll do it. It's painful, but I'll do it. Why not? Okay, so negative h bar squared over 2m. Okay, so now we want to know what's the first derivative of psi with respect to x on the positive side. Let's see, on the positive side, we've got this equation. So I'm going to differentiate this with respect to x. That brings down a factor of ik in the first term. It brings down a factor of negative ik on the second term. And then I'll take the limit as x goes to 0. So then these exponential factors are going to go to 1. Okay. So this gives us an IKF minus IKG. Okay, now I want to do the same thing for the function on the negative side. That's using this. Okay, so that gives us minus, IKA minus IKB. All right. And then minus alpha psi at 0. Well, that is a plus b, or equivalently, it is f plus g, either way. So that equals 0. Okay, so this is another equation involving A, B, F, and G coefficients. Okay, so let's see, can I simplify this? Maybe. Let's see, if we have negative h bar squared over 2m, let's see, if I factor out an ik, and this is f minus g minus a plus b, okay, equals alpha a plus b. Right, well, what do we get here? I guess there must be a trick. I did this before. It worked, but I did it before. So negative, what was the trick? Okay, I know I had a good trick for this. Let's get F and G on one side and A and B on the other side. All right, so negative h bar squared ik over 2m f minus g is equal to h bar squared, negative h bar squared ik over 2m a minus b plus alpha times a plus b. Okay, and then what? I'll multiply through by this reciprocal, okay, and the reciprocal of this thing, okay. So I get then f minus g is equal to a minus b, and then minus alpha ik h bar squared over 2m times, wait a minute, yeah, that's what this is, times a plus b. Okay, I think that's what I wanted, maybe. All right, and then what? Then, so this tells us something about f minus g compared to a and b. So this is a times something and then minus b times something. Okay, so it's a times 1 minus alpha ik h bar squared over 2m, and then b times 1 plus alpha ik h bar squared over 2m. Right, okay, well, looks a little bit different from my notes somehow. Something is different, but what?
The numerator and denominator are opposite. This should be flipped.
The denominator, oh yeah, good point. Thank you.
You're welcome.
Okay. That's this thing, right? Okay. That was always the highlight of the day for me when I was a student, if I could catch my professor's mistakes. And so I need to do some on purpose so that you can have that pleasure. All right, so good. Okay, so what is this? 2m over ik h bar squared. All right, 1 minus 2m over ik.
Shouldn't alpha still be there?
Oh yeah, and there's an alpha, like that, okay. 2m alpha over ik h bar squared. Right, okay. Maybe that's right. Okay, and then if I wanted to be compatible with the book, then the book defines a variable beta as m alpha over h bar squared k. Okay, so that's this thing or this thing. Okay, and then the book would say f minus g is equal to a times 1 minus 2 something, 2 beta over I. Okay, and then minus b times 1 plus 2 beta over I. Or if I want to put the i's in the numerator, it'll look nicer. 1 plus 2i beta minus b times 1 minus 2i beta. Okay. All right. That actually comes out to be the same as what was in my notes. Huh, it's a miracle. All right. F minus G is that. Okay. And F plus G is A plus B. Okay. So we have 2 equations in 4 unknowns. Oh, well, that's not enough equations. All right. So we have some constraints on these things, but it looks like there's going to be a lot of solutions, really a big family of solutions. So if we want to interpret this, I'm going to take a break and say, what is a scattering state anyway? What is a scattering state anyway? That's my break from this calculation because I'm tired of it. What is a scattering state anyway? All right. A typical physics experiment is a scattering experiment, right? That in physics, we do lots of scattering experiments where we study a system by sending in some input and to see what comes out, okay? And so that is something, that happens in high energy physics, right? Where people build these giant particle colliders and we make collisions and see what are the results, okay? It happens in lower energy scales where we do X-ray diffraction experiments or light scattering experiments, right? Where we shine a laser on a sample and see how the light is scattered by the sample and learn information about a sample that way, okay? And that is the reason why an unbound state is often called a scattering state, right? The point is that it's not that scattering is happening everywhere in nature, but it's happening everywhere in physics, right? It's happening in what physicists do, right? It's part of the typical experiment that we do. And so we develop a formalism to analyze this kind of experiment. And so that's why we use this language in classical mechanics also, right? That we refer to an unbound state, like a spacecraft that's on some escape trajectory as a scattering experiment, even though, when we're launching a spacecraft, that's not really scattering, right? The scattering version would be like if the aliens are studying us by throwing asteroids at us, right? They shoot asteroids at us to see what we're going to do, right? And so they're scattering asteroids off of Earth, and they're going to see what the output is. Okay, so let's suppose that what we want to study is the delta function potential. Right? If the delta function potential represents some kind of atom, right, that we're investigating, okay? And so we're studying it by shooting waves at it in one dimension. And we want to see what's going to happen, okay? So here's my drawing of the delta function potential, same as I had before. Okay, so there's the V of X as a function of X, and the potential energy looks like this. Okay, so let's suppose we're going to do a scattering experiment to study that. Okay? So that means that we have some kind of source over here. And that is sending waves towards the potential, okay? And so it is making particles or waves, right? Like wave packets coming in like this, right? And that is headed towards the delta function potential. Now, that particle will interact with the delta function potential that is sitting there. And then, what can happen? Well, one possibility is that it can get through. Okay, so you can have more waves coming out in this direction. This is what we would call transmittance. Okay. Another possibility is that the wave could get reflected off of the potential and head back towards the original source. Okay, so we could have something like this going back towards the source. Okay. That is called reflectance. So these are the only two possibilities in one dimension. Right? In 2 dimensions or 3 dimensions, there could be a lot more possibilities. Right? The particle could get scattered in any angle. There'd be a lot more to calculate. But in 1 dimension, really, it's only these 2 possibilities. Right? The particle can go forwards or it can go backwards. So the idea here is we want to know of the waves that are coming in, how much is getting transmitted and how much is getting reflected. Okay? So this is similar to what you might have done with waves on a string. Well, let me ask you, was this part of what you studied, say, in university physics or other physics classes at Kent State, right? To say, suppose you have a heavy string connected to a light string, right? And you put in waves on the heavy string and it hits the interface. Some of it gets transmitted, some of it gets reflected. Do you have any idea of what I'm talking about there? Is that's part of what you've studied so far? Was that in university physics or another class? University? Yes, okay. All right, well, you know from when you studied that, right, that there is some transmittance coefficient that says how much gets transmitted, right? And a reflection coefficient that says how much gets reflected, okay? So that's what we could try to figure out here, okay? We could try to say, if we have a certain wave coming in, how much is going to be transmitted and how much is going to be reflected, okay? So let's try to think about that in terms of these four coefficients, A, B, F, and G. So on the left side, that is negative X, we have this combination of waves, right? So there is a wave moving to the right and a wave moving to the left, right? So A means the wave moving to the right, and B means the wave moving to the left. Right? So in our picture, that means A is the amplitude for the wave going to the right, okay? So that's this thing. The amplitude A is for this wave going to the right. It's the wave coming out of the source, okay? It's the input. Okay, then B is the amplitude of the wave going to the left on the negative X side. So that's over here. It's the reflected amplitude is B. Okay. And now what about on the other side? So the positive X side, okay? On the positive X side, we think F is the amplitude of the wave going to the right, and G is the amplitude of the wave going to the left. So that means there is a transmitted amplitude is F, and then, well, there is no wave going to the left on this side, right? There's nothing happening over here because the way we've designed this scattering experiment is that the source is coming in from the left, right? So the calculation doesn't know that, right? The algebra would work if we put the source over here, or we could put the source over there, right? The algebra works both ways, but the application of the algebra is to say the source is over here and the only input is A, okay? So that means that we must have G equals 0. Okay, so that says that in our scattering experiment, we want to find F and B, okay, the transmitted amplitude and the reflected amplitude, okay? And we want to find those things in terms of A, right? We input A, and we want to find F and B with the assumption that G equals 0. Okay, so if we put it that way, then we have these two equations up here. And we're going to put in G equals 0. And we want to solve for F and B in terms of A. Okay. So we still have two equations, okay? But now we just want to solve the two equations for two unknowns. And that is actually a solvable problem. Okay, so let's do it. Let's solve it. Okay, so we have these two equations. Okay. Copy. Paste. Ooh, it works. Okay, so if we have those two equations and we are going to set G equals 0. Okay, so now we have F equals A plus B, and it also equals A times 1 plus 2i beta minus B times 1 minus 2i beta. Okay, so let's see, we can solve for B, I guess. Okay, so how do we do it? Well, let's put the B over on the left side. So B times 2 minus 2i beta. And we'll put the A on the right side. That's equal to A times 2i beta. Therefore, B is 2i beta over 2 minus 2i beta times A, right? Or if I cancel the 2's, that is B equals I beta over 1 minus I beta A. And then we can get out F also. So F is then A plus B. So that is A times, well, we'll put everything over this denominator, 1 minus I beta. Okay, and so it's 1 minus I beta, that's the A part, and then the B part is plus I beta, and those things cancel. So F is 1 over 1 minus I beta times A. Okay, so this tells us that the reflected wave, B, is proportional to the input. And the transmitted wave, F, is also proportional to the input. Right? And that makes sense, right? And that's just like the waves that you studied in university physics, where, again, the transmitted and reflected waves are both proportional to the input waves. And back in that course, you defined things like the transmission coefficient and the reflection coefficient, right? Okay. I say right, and you say right. Okay, right, yes, you have confidence. Okay, so you had things that were like the reflection coefficient. And that is R, right? And so that is the probability that the wave is reflected. So it's a probability, it's the amplitude squared. So it's the b squared over a squared. So that is the b conjugate times b divided by a conjugate times a. Okay, so that is what it's, well, I figured out b over a here, right? Okay, that's this ratio. So b over a is I beta over 1 minus I beta. That's b over a. And b star over a star is the complex conjugate of that thing. All right, so it's negative I beta over 1 plus I beta. So it is beta squared over 1 plus beta squared. Okay, and then there's also a transmission coefficient. So that's T, we could call it, the probability that the wave is transmitted. Okay, so by the same kind of argument, that is F squared, F magnitude squared over A magnitude squared. So that is F star F over A star A. So let's see, F over A is 1 over 1 minus I beta. And the complex conjugate is 1 over 1 plus I beta. And so this whole thing simplifies to be 1 over 1 plus beta squared. And you will notice if you compare these two expressions that you can see that R plus T is equal to 1. Right? And so that is to say, everything that comes in either gets transmitted or reflected. Right? There's a conservation of stuff. Right? And so we can look and see, right, that the total amount of probability is not increasing or decreasing, right? It's just staying the same, right? We could also go back and refresh our memories about what is this parameter beta anyway, and then try to interpret it in terms of energy. Okay, so beta, what is beta? Well, we defined it a long time ago, somewhere here. Not there, not there. Here it is. Okay. Beta is this thing. Last sentence. Here it is. Beta is this thing. Copy. Okay. So, right. Beta is this thing. Okay. And the K is expressed in terms of the energy, right? Remember, we also defined that k squared is 2me over h bar squared. Okay, so that means k is the square root of 2me over h bar. Okay, so beta depends on energy, right? So beta is m alpha over h bar squared times this square root 2me over h bar. Okay, what can we do? We can cancel the h bars, and then this is alpha over h bar, and then there's a square root of m over 2e. Okay. So beta squared is m alpha squared over 2 h bar squared e. That's what I was looking for. Okay, so beta depends on the energy of the particle. So the particle coming out of our source has some energy. That's in the denominator. Okay, compared with the alpha, that's the energy associated with the delta function potential. Okay. So then we have that the reflectance coefficient is beta squared over 1 plus beta squared. So I guess I could write that as 1 plus beta to the minus 2. This is 1 over 1 plus, I'll put the inverse here, so 2 h bar squared e over m alpha squared. And likewise, the transmittance is 1 plus 1 over 1 plus beta squared. So it's 1 over 1 plus m alpha squared over 2 h bar squared e. Okay, so the point of doing this is to say, what happens if we vary the energy? So if we have a higher energy, then this denominator gets bigger. So there's less reflectance, more transmittance. More transmittance. Okay, so that kind of makes sense, right? If we're shooting the particles from our source at a higher energy, more is going to get through, less is going to be reflected. Okay. On the other hand, if we're shooting the particles from our source at a lower energy, then less will get through, more will be reflected. Okay. So that's something else that comes from this calculation. Okay, so we've learned several things here. So I'll summarize with the highlights of our results. Okay, so the delta function potential has both bound state and scattering states. Okay, and we know how many. It has exactly one bound state with a specified energy and a specified kappa, that is the length scale of how far away from the origin can the particle go. Okay, and it has infinitely many scattering states. And we also found that the scattering states are continuous. That is, we can have any value of k on the number line. But the bound state is discrete. That is, we can count it. We can count it on our fingers. We can count it on one finger. There's one of them, okay? But even if there's more than one, we could say, what are the allowed values of kappa? Value number 1, value number 2, number 3, etc. Okay, so those are general principles in quantum that we can have both kinds of states like this, and that the bound states are discrete and the scattering states are continuous. Okay, now I told you back when we started on this big calculation that the delta function potential was like an easier version of the golf course potential, right? That the delta function potential is one where there's a really sharp spike going downwards in the plot of v of x. And by comparison, what I call the golf course potential is one where v of x has, this shape where it has some finite width and it has a finite depth. We can solve the golf course potential, but it is more work. Okay. The reason why it is more work is basically that there are two interfaces, right? That the delta function potential, has one interface at x equals 0, but the golf course potential has two interfaces there and there. Okay. So if we want to solve it, we want to solve it in this region, and then in this region, and then in this region. And then we need to join the solutions together there and there, right? And so we will have two coefficients there, and two coefficients there, and two coefficients there, right? So 6 coefficients in all. And then we'll have equations at this boundary and this boundary about how to join them up and how to relate all 6 of those coefficients. That is now a little too much work for me to do. I don't have time to go through all of that in this semester. But it is written up in the textbook, okay? And so if you want to go look for it in the textbook, this is in section 2.6. And it gets a better name. They don't call it the golf course potential there. They call it the finite square well. Okay. Finite because the height of the potential, like that, is finite, right? Unlike the particle in a box where the height goes to infinity. And so that's the finite. And square well means just that the plot has right angles like this. So that is treated in that section of the book. And so you can see how it all works out. It's basically similar to the results from the delta function potential. The main difference is that there can be more than one bound state. Depending on how wide is the potential well and how deep is the potential well compared to the energy of the particle. There will always be at least one bound state, but there might be multiple bound states in addition to the scattering states. Also scattering states. So, you know, there's a big calculation that leads to those results, and you can look it over. I'm going to skip over that because there are other things that I want to get to. Okay, so for me, this is the end of chapter 2. Okay, so I'm going to stop talking about chapter 2 now, which is the chapter about solving Schrodinger's equation in various one-dimensional situations, right? So with one-dimensional potential energies. Okay. And beginning tomorrow, I'm going to move on to chapter 3. Okay, so the purpose of chapter 3 is to actually do something that's a little bit of a break from solving Schrodinger's equation. Okay, so chapter 3 is designed to set up a general mathematical framework for quantum mechanics. And it's a framework that will lead us to a nice compact notation for wave functions. It's more compact than what we've been doing so far in the course. Okay? So I'm going to talk about some general mathematical principles about how quantum mechanics is like linear algebra and how wave functions are like vectors and how operators are like matrices. And so we're going to have a few weeks with going through those kinds of mathematical principles. And then after that, using that information, we're going to get back to solving Schrodinger's equation, but in 3 dimensions instead of 1 dimension. And so, you know, we'll be able to use that notation to deal with 3-dimensional problems. Okay, so this is the end for chapter 2, and the homework that I assigned is the last homework for chapter 2, which will be due a week from today, so March 1st. The last thing I'll just briefly mention for today is that I'm going to need to make a plan for the midterm. Okay, and so in the syllabus, I wrote that the midterm would be tentatively scheduled for March 12th. That date is still okay with me. I want you just to think about whether that date is okay with you, or if that date makes trouble for your other classes. So I will ask you about that tomorrow, okay? So for tomorrow, think about, you know, is March 1st an okay date for the midterm? It's going to be a 24-hour midterm, so say from noon to noon or something like that, right? And so is March 12th, whatever I wrote in the syllabus, is that still okay as a date for the midterm? And if so, great. If not, tell me some alternatives that work better for you. Okay, so we'll talk about that tomorrow, and then we can talk about the beginning of chapter 3. Okay, I will stop for now. I will see you guys tomorrow. Thanks.